Good day, I'm Maile Madziba. Welcome back to our channel. Today we're starting with clusters 2 of 2011 of our CIR 123 module. So we're looking at part 1 of this clusters 2. It says the following gas phase reaction is studied in a batch reactor. A plus 2B equals to 3C plus D. And it goes further to say the following unwanted reaction also takes place. D equals to 2B plus A. Now it goes further to say unknown quantities of A and B were charged to the reactor, and after 3-hour reaction time, the gas mixture was analyzed. The analysis showed 25% A, 20% B, and 10% D. Now the question says, calculate the excess reactant based on reaction 1, which is the excess reactant based on this reaction. So now with that said, I've actually outlined a couple of steps to actually answer this question in full. So before we go far, I think what we need to do now is to just choose a basis. Or let me just write basis. And we choose 100 kilomole of the gas mixture. It's gonna be much easier. 100 kilomole gas mixture after 3-hour reaction time. That is actually 100 kilomole of this mixture here. And with that said, if this is 100 kilomole, then our A becomes 25 kilomole, and our B becomes 20 kilomole, and our C, I'll come to it, and our D becomes 10 kilomole, and our C becomes 100 minus 25 minus 20 minus 10, and that gives you 45 kilomole. So now we know that after 3 hours reaction time, we have this analysis. Now, moving forward, we go to our step 1. Step 1. So in our step 1, what we're going to do in our step 1, we're going to calculate the amount of A and B that reacted and also the amount of D. Remember, C was not disturbed or was not changed in these two reactions. If you can check here, A and B and D also are involved here. So they cause a little bit of a confusion, but D was not tampered with. So we can actually use D as a standard, especially because we know that after 3 hours, we have 45 kilomole of C. So with that said, let me just outline the step here. Calculate the amount of A and B that reacted and D that was formed from reaction 1. So in the first reaction, we want to know how much of A and B reacted and how much of D had actually produced. And for us to easily get that, we're going to use C like I explained. And let me just highlight here that since C is unchanged, therefore we can actually use the ratio of C and A and then to calculate A. So therefore, the ratio of A and C is 1:3, right? Therefore, A that reacted is equals to C over 3, and that is equals to 45 kilomole over 3, and that gives you 15 kilomole. So that then becomes our A. Now, out of so far we have figured out that A has 15 kilomole of A has reacted. Now let's do the same with C. So let me just put this aside and I'll just keep bringing it back. So therefore, I can go now do the same with C. The ratio of B and C is 2 to 3. This is according to this equation here, and let me just bring it to you. This is according to this reaction equation here. The ratio of B and C is 2 to 3. Therefore, B reacted is equals to 2 multiplied by C all over 3, and that is equals to 2 multiplied by 45 kilomole all over 3, and if you use your calculator, that gives you 30 kilomole. So now we know that 15 kilomole A reacted and also 30 kilomole B reacted. Now we do the same to get how much of D that was produced. The ratio of C and D is 3:1. Therefore, D produced is equals to C over 3. Then that gives you 45 kilomole all over 3. And if you use your calculator, that becomes 15 kilomole. Let me just revisit the question a little bit just to clarify something. Remember, now we know here that according to our calculation or what we found that 15 kilomole A reacted and 30 kilomole B reacted, and also we've just found out that 50 kilomole D has been produced. But now it's important to understand that the 15 kilomole A and B that we actually calculated here is not what was put in the reactor initially. So this is just what was reacted. So we still need to know that how much of A and B had actually, or how much of A and B was put in the reactor in the beginning. And having found out these few values is going to actually help us, or is going to lead us to figuring out or finding out how much of A and B that was put. And when we know the A and B that was put, then we can start looking at which one is in excess, and then we can then calculate the percentage access for the one that is actually in excess. So I just found I needed to clarify that. Now with that said, we are done with our step. Remember our step 1, we said that we calculate the amount of A and B that reacted and also D that was formed. So we are done with that. Then we go to step 2. Step 2, it says calculate the amount of D that reversed into A and B in the second reaction. So a little bit of an explanation. Now our step 2 says, now that we know how much of the information we got, now the second reaction says D, after D was formed here, part of this D actually reconverted or decomposed to 2B and A. So we want to know how much of this D decomposed to 2B and A. And that is actually what we're going to do. And for us to get that, I just put together like a little bit of an equation here, and then I'll explain it. So let me just write it. V that is left after 3 hours reaction time is equals to D that was produced, right, in equation 1. Let me write it underneath, minus the D that reversed into A and B in equation 2. I hope it's visible. I really hope it's visible. Well, let me just say in equation 2. Let me just explain it. So here the equation is actually saying the D that was left, the D left after 3-hour reaction time. This is actually the D here. Where is it? Yeah, let me bring it here. This is the D here. This D here. Where does this D come from? It's actually the D that was produced, is the D that was formed from the reaction equation here, right? And then minus the D that reversed. So we are basically saying the D that we are, the 10% D here, or the the 10 kilomole D here after the basis, is actually the D that was produced minus the D that decomposed back to B and A. So that is actually the basis of this reaction equation. And if you move further, to simplify it, I can just say the D, I just made rearrangements. The D that reversed into A and B is equals to the D that got produced from equation 1 minus the D left after 3 hours. So now I just rearranged this and made this one to be the subject of the formula, because the equation, what we are calculating, we are saying we are calculating the amount of A that was reversed into A into the second reaction equation. So with that said, I can actually just substitute values. The D that was produced from equation 1, we figured it out to be, we did calculate it, let me see. It's actually here, it's 15 kilomole. So it's 15 kilomole minus the D that was left after 3 hours, after we chose a basis of 100 kilomole, and that becomes 10 kilomole. So it's 10 kilomole. And now if you use your calculator, it gives you 5 kilomole of D. Now this tells us that in this second reaction equation here, this D that converted to 2B and A is actually 5 kilomole. Now we are done with step 2. This takes us to our step 3. Step 3. Let me just write it down. Now that we know that the D that decomposed is 5 kilomole, then we can actually calculate the B that formed and the A that formed out of the 5 kilomole. And that is our step 3. So calculate the amount of A and B reproduced from reaction 2, right? And if we look at reaction 2, we can actually use the ratios, because we already know that this is 5 kilomole. So the ratio of, can I just put it here? The ratio of D and B in reaction 2 is 1:2. Therefore, B produced, let me say reproduced, B reproduced in equation 2 is equals to 2 by D is equals to 2 multiplied by 5 kilomole, and that makes it 10 kilomole. So now we know that the B that was reproduced in this reaction is actually 10 kilomole, and then we do the same with the A, and then we can just say the ratio of D and A in reaction 2 is 1:1. Therefore, A reproduced. Therefore, A reproduced from reaction 2 is equals to D and is equals to 5 kilomole. So the A here, you can see the ratio is 1:1. So if this is 5 kilomole, then the A produced is also 5 kilomole. So now we are done with our step 3. This takes us then to our step 4. So can I just bring in a new page? So now going to our step 4. Let me just write it down. In our step 4, we're going to calculate the amount. Now we're getting closer to answering the question. We're going to calculate the amount of A and the amount of B that was initially loaded in the reactor. So we want to know how much of A and B that has been loaded initially before the reaction. So calculate the amount of A and B that was initially loaded in the batch reactor. That is actually what we're going to be calculating. Now, there's also another equation that I just made up, so I'll just explain it. Let me just write it here that A initially loaded, I'll explain it afterwards. A initially loaded is equals to A reacted minus A reproduced in equation 2, right? A reacted minus A reproduced in equation 2 plus A that is left after 3 hours reaction time. Yeah, I just need to explain that a little bit. So remember, the A that was initially loaded here, what is it? Is the A that reacted, which is the A that was consumed to form this, and then plus the A that was reproduced, in the second reaction equation, and also plus the A that was left in the reactor after 3 hours. Remember that let me bring that first one. Remember, we have an A already here, which is 25 kilomole. You see, so this is actually after 3 hours. You see the A that was left in the reactor. So this is actually the reaction equation. And for us to be able to how do I put it? For us to be able to figure out the A that was initially loaded, we can just substitute the values. So it's equals to the A that reacted. We calculated the A that reacted to be, where is it? It's around, the A that reacted is 15 kilomole. And then the A that was reproduced is minus 5 kilomole. And the A that was left after 3 hours is plus 25 kilomole. Then if you use your calculator, it gives you 35 kilomole, right? So the A that was initially loaded is actually 35 kilomole. Now moving further, we do the same with the B. So the B initially loaded is equals to B that reacted, right? And then minus B reproduced in equation 2 plus B that is left after 3 hours, right? So yeah, and then if you substitute the values, you get the B that reacted, we know it to be 30, we just calculated it is 30 kilomole, and then the B that was reproduced from the second reaction is 10 kilomole, and then the B that was left, the B that was left becomes, is plus 20 kilomole. Because if you check, according to the basis of 100 kilomole, the B that was left is actually 20 kilomole. And if you use your calculator, it gives you 40 kilomole. So now with that said, we can just safely say, therefore, initially, 35 kilomole A and 40 kilomole B was loaded into the reactor. Right? Now, with that said, we are done with our step 4. This takes us now to our step 5. Step 5. Now, in step 5, we're going to calculate the excess reactant in the reactor. Calculate the excess reactant in the reactor. Now that we know that our A is actually 35 kilomole initially, and also our B was 40 kilomole, then we can actually know which one is in excess and then calculate the percentage excess. So with that said, now we're going to just use the ratios and say the ratio of A and B in reaction 1 is 1:2. Therefore, for 35 kilomole A, we need 70 kilomole B. Now with that said, okay, let me just say, but we have 40 kilomole B, right? Now with that said, therefore, A is the excess reactant and B is the limiting reactant. So that is actually what we have concluded, that because we have 35 kilomole A and 40 kilomole B, that makes A the excess reactant and B the limiting reactant. Now this takes us to our step 6. Step 6. Now in step 6, we calculate, now that we know which one is in excess and it's A, then we calculate the percentage excess. I can just say calculate the percentage excess A, right? Therefore, percentage excess A is equals to total kilomole A, right, before reaction, right, minus kilomole A. I need to highlight here that theoretically required, and all over kilomole A theoretically required, right? And everything else, I don't have space, and everything else multiplied by 100%. But let me just rewrite it here. So percentage excess A is equals to the total kilomole A. If you use your calculator, we find that originally there was 35 kilomole. we just calculated it to be 35 kilomole, and then minus the kilomole of A theoretically required, you'll find it to be 20 kilomole, and all over kilomole A theoretically required is 20 kilomole, and multiply by 100%. Now, therefore, percentage access is equals to 75% if you use your calculator. Now, the kilomole theoretically required should not be difficult. I just made a simple calculation that I can actually share with you here. How to find the kilomole of A theoretically required. Here is it here. So you can just say the ratio of A and B in the reactor in the first reaction equation is 1:2. Therefore, for 40 kilomole B, you need 20 kilomole A. Therefore, theoretically required A is actually 20 kilomole. So that is actually how to find it, and that's how I've actually found this 20 kilomole here. And then if you use your calculator, it gives you 75 kilomole. So this is it. So yeah, thank you for your time, and I hope we meet again in our next video.